Alright, we're going to talk a bit about hypothesis testing. I've had a few questions about this. I've had a few requests to make a video. Now, first of all, a lot of people wonder what's the difference between hypothesis testing and confidence intervals. Now, here's the thing with a confidence interval. Confidence interval, you have a population you want to know something about. You want to get a parameter out of it. But you don't want to ask everybody. Don't want to do a census. Way too much work. And say your population, you have no idea. Like we're going to talk about today, ghosts. What percent of Americans believe in ghosts? Say we have no idea going into this. Could be 50%, could be 80%, could be 2%. We really have no idea. We can't ask the entire U.S. population. It's unrealistic. Can't do a census. So what do? We do a random sample. And ideally, that random sample is going to look something like your population. You always want your random sample to resemble your population. If you do a good one, it should. You get a statistic. Now, an uneducated statistician might say, okay, that's enough. Let's generalize that. You don't want to do that. There's variation in sampling. So what do? We create a range of values that could capture that parameter. You take that stat. You go down a bit, you go up the same amount. That's your margin of error. And that creates a range of values where that parameter could fall into. Like say, I'm just making this up. Say I ended up getting 36%. Maybe I say I want my margin of error of 12%, so it goes down to 24 here. Go up to 48. I can say I had 90% confidence interval. I'm 90% confident that the actual parameter of U.S. adults who believe in ghosts is somewhere between 24% and 48%. Now I have a generalized idea of where that parameter could be. That's a confidence interval. You have no idea what the parameter could be, so you decide, okay, I'll get a statistic, use my margin of error to create a range of values, and boom. You got yourself a possibility. Now, hypothesis testing, that's when you have some sort of idea of what that parameter could be. Maybe it's from a previous study. Maybe someone tells you and says, hey, I heard it's 45%, the case what we're doing right here. You maybe read it from a study or something. You have something to go off of. That's when you do a hypothesis test. Like in this case, if you read the problem, it's believed that from past studies, 45% of adults in the U.S. believe in ghosts. You think that number is too high. So you have a parameter that you assume, but then you're going to try and prove otherwise. Maybe you're trying to prove it's more, it's less, or maybe that's just not the parameter they assume. Like maybe I want to prove that's not 45%. Either case, that's a hypothesis test. So what am I going to do here? I'm going to establish a null hypothesis of that the parameter is 0.45. And I'm going to say, you know what? I'm going to make this nice and easy. I'm going to highlight this in purple, save myself some writing. Now, typically, you should actually, do this. But I'm just doing this for the sake of time. Adults in the U.S. who believe in ghosts, we're going to say proportion of, and we're going to say that's P. Being a little lazy here, but... All right, so now for my alternate. I'm trying to prove that it's less. That's your alternate. Your alternate's always going to be either less than, greater than, or doesn't equal. Your null is always going to be an equal statement. It's something you're going off of. Now, hopefully you learned this a little bit before you started doing confidence intervals and hypothesis testing, but you have sampling distributions. What that is that's a collection of possible statistics you could get. That's what we're going to go off of here. It says we do a random sample of 1,012, so that's all I'm concerned with now. I do not care yet how many of those 1,012 said, okay, I believe in ghosts. Because I'm going to create a sampling distribution, a collection of possible statistics I could get if the parameter is actually 45%. So if it's actually 45%, if it's really true that, 45% of people in the United States believe in ghosts, if I do a sample size of 1,012, I could get that 45%. But I probably won't. It's not that likely. Thing is, there's variation in sampling. You're going to get some different numbers, but you should get something relatively close. Is it possible you don't get something close? Sure, but the probability of that happening is really low. So you notice I'm drawing all these p-hats. These are statistics. These are all possible statistics I could get. Maybe I get, these represent getting 45%. I ask, boom, I get 45%. Maybe I get something really high. Maybe I get something really low. It's all possible. And that's what a hypothesis test is based on. You create a sampling distribution off of that parameter that you assume. Now, I already calculated the standard deviation. I got 0.016. How did I do that? I used my null hypothesis, that assumed parameter, use my formula here, probability of success, probability of failure, divided by sample size. So now I'm going to draw a sampling distribution based on that. So I got 0.016, and I hope my math is right. Should probably use a calculator. 434. And ideally, you probably are too. And you know what? Just for this one, I can't do this in my head, so I'm going to plug it in. All right, 0.418. All right. So now this represents all the statistics I could probably get. Now, I made a dangerous assumption here. I assumed the sampling distribution was normal. That's why we use our conditions. We have to prove that it's going to be normal. So what are our conditions? Again, hopefully you learned this when you did sampling distributions. But if you want to know if a sampling distribution is normal based on a population, you want to make sure that it's a random sample. Is it? Looks like we did a random sample of 1,012. Ideally, you want to walk through, quote it, write this out, but for the sake of just keeping things moving, I'm going to be pretty quick with this. 10%. I want to make sure that 1,012 is less than 10% of all Americans. I think it is safe to say that 1,012 is less than 10% of all Americans. Going out on a limb here. Large counts. This is where the biggest mistake comes in. Notice I have not even taken our statistic into play yet. This is all going to be based on my null hypothesis, or that parameter that I'm assuming. So, 45% of 1,012. Is that greater than or equal to 10? Yeah, very safe to say. And likewise, 55% of 1,012 greater than 10? Absolutely. So I'm looking at more than 10 successes, or 10 successes or more, or 10 or more failures. In this case, a success, they believe in ghosts. A failure, they don't. Now, I'm going to take that statistic into play now. The statistic we actually got, which in this case was 433 out of 1,012. 33 divided by 1,012. The statistic we got, 0.427. That's going to fall somewhere in here. Now, this hypothesis test, we're trying to find the probability of getting our statistic at 0.427 or less. So that represents all these statistics, that or less. Why less? That's what we're trying to prove here. We're trying to prove that the parameter is actually less. So we find the probability of getting our statistic or less. That is our p-value. The probability of getting the statistic you see or less in this case. If you're doing a hypothesis test to prove that the parameter was greater, if you want to look at the probability of getting that statistic or greater. Two-sided test, then you're looking at the probability of getting a statistic that drastic in either direction. I have a nice little video up about two-sided tests that can walk you through that a little bit. But for p-value, there's a nifty little calculator function. You can do one prop z test. However, this is a nice way of doing it. You're going to use norm CDF. Find the percentage of all values less than your statistic in this normal distribution. So I'm going to go with negative 999 all the way over here, because that's, all the way down. It represents all those low statistics, all the way up to 0.427. So lower, notice I'm labeling these. If you're an AP Stats student, this is important. You want to make sure you're labeling on your AP exam. And then you got your 0.45, which is your mean, standard deviation, 0.016 SD. Let's find the probability of getting that statistic or lower. Negative 99999. 0.427. 0.45. 0.016. All right. I get 0.075, I think. Yep, somewhere in that ballpark. So that means probability of getting this statistic or less is about 7.5%. What that's telling me is I really shouldn't be getting that statistic if that 45% is true. However, this is where the significance level comes in. Where do you want to set that significance level? Sometimes people set it to about 10%. They'll say, we're going to reject 10% of all possible statistics, the lowest 10%. Because you have to draw the line somewhere. You have to say, when am I going to start believing that this 45% isn't true? And a lot of times, sometimes you could think, well, maybe you're a pretty firm believer. It's going to take a lot for you to believe. So you want something, really low. If that's the case, you want a really low significance level, which means you're going to reject all the stuff way down here. Maybe you're a little less skeptical. You're looking for something to disprove that null. In that case, you could set your significance level all the way up here and say, I'm going to reject everything to the left. If I get anything on that left side, then I'm going to reject my null hypothesis. Statisticians, we typically like that 5%. So that's going to fall somewhere about right here based on my distribution. So if we say any of those lower 5% of statistics, we're going to say that's so unlikely, we're going to disprove our null hypothesis. However, in this case, we got something that's 7.5%. And we're going to set that significance level to 0.05. Again, you could go with 10%, you could go with 1%. I've seen these different, but typically you're going to see 5%. So you want to see if getting that statistic if you're going to be seeing that statistic 5% of the time or less. Unfortunately, or I hate to say unfortunately, we got a statistic that we're going to see 7.5% of the time or less. Unlikely, but it did not fall into that rejection zone we created. It is not unlikely enough for us to dispute that 45%. So this is where your conclusion comes in. Since our p-value is greater than our significance level, we fail to reject the null. Now, notice we are not accepting it. You don't accept it in a hypothesis test. All you do is you fail to reject the null. You never accept the null hypothesis. Reason why? We just don't really have enough evidence. Maybe we could do another sample. Maybe we do get something more unlikely. Then we can say that 45% is true. But we're not really in the position to be accepting it. All we can say is we don't have enough evidence. Again, I'm sorry I'm running slower than I'm speaking. To prove that less than 45% of Americans believe in ghosts. We have no proof to dispute that now. If we had a lower statistic, we might be able to. If the probability of getting another statistic was less than 5%, like say we got one of these statistics in here, we got one of these, then we'd have enough evidence to say, okay, I got something really low here, so that 45% is bogus. But we didn't. We got something just to the right of it. And that's the gist of hypothesis testing. You have some sort of parameter. You're either trying to prove that the parameter isn't true because the actual parameter is greater or less, or it's just not equal to whatever you assume here. And that's why you do hypothesis testing. Hopefully this helps you get the idea of how it works, where the whole thing comes from. Because a lot of times I've seen, in my years of teaching statistics, I just see kids plug it into the calculator, get a p-value, robotically write out a statement, and they have really no idea what it is. Hopefully this helps.